Start with my motivational problem. That's not concordance. Well, some of you or many of you are familiar with this notion, but let me remind you. So let me give you a schematic picture. Okay, this is my knot K in S3, let's say. And I have another one. Let's say K prime. Well, I have two copies of S3, and so let me view this as S3 cross 0 and cross 1. Okay? Well, I'm going to think of a kind of four-dimensional deformation of this knot. So I think of this full space, and then if, well, there is a embedded submanifold C, which is the cylinder, then by definition we say that K and K prime are concordant. Okay? This is the definition of classical knot concordance. And this generalizes to several other cases. For instance, I can think of links, namely more than one component. And then the two concordant links are joined by disjoint union of annuli, and so in particular they have the same number of components. And also we can think of higher dimensional situation and general manifold embeddings. Namely, this is the case of an embedding of S1 into the standard 3 sphere, but I can also think of a given fixed manifold M and its embedding into another fixed manifold N. And then I can also think of this kind of relation, which is also referred to as concordance. Well, so generalization includes links and general manifold embeddings. Well, and if K, we say that K is a slice knot if K is concordant to the trivial knot. Okay? And this holds if and only if K bounds a Q-disk embedded in the full ball whose boundary is the ambient space of K, namely S3. Okay? So if K prime is trivial, then I can just kept the annulus to get a disk. Okay? So this problem is originally proposed by, well, the problem is to classify knots up to concordance. And this problem was originally suggested by Fox and Milner in the 60s. And this is related to various other problems in geometric topology. For instance, as pointed out in the recent paper of Friedman, Gompf, and Walker, and who was the last author? Morrison, right? Thank you. If I can understand smooth link concordance and knot concordance, then we may be able to give a counterexample to the smooth four-dimensional Poincare conjecture, but unfortunately, well, their potential counterexamples were proven to be the honest four-sphere immediately by Archibald. Another important problem related to this is the topological surgery problem for full manifolds. Friedman proved that topological surgery works for full manifolds in the simply connected case and some generalized cases whose fundamental groups are easier to deal with, but in general, the answer is not yet known. And if we can completely understand the classification of link concordance, then we can give an answer to that question. I will focus on this problem. So, there is a very systematic framework to study concordance. Given a knot K, I can think of the exterior. The exterior is none more than S3 with an open tubular neighborhood removed. Then it turns out that, well, if two knots are concordant in this case, in this way, then I can also get rid of this concordance from this four-dimensional space. And then the result is certain four-dimensional manifold W, where, well, let's say this is the manifold obtained from K, and this is the manifold obtained from K prime. And from the concordance, I can get a four-manifold W, which is a cobordism between them. And actually, it turns out that this is a homology cobordism. Namely, the inclusions induces.
What did I say? Sorry.
This is something like this, yeah. So this, or if you like, if you prefer to deal with closed three manifold, then I can also think of the zero-framed surgery. So this is my MK, either this or this. Okay. Then, I mean, W is a homology cobordism by definition if the inclusion maps induce isomorphisms on integral homology. So, in order to understand concordance, I need to investigate this relation between three manifolds. Actually, the classification of exteriors up to homology cobordism is almost the same as the classification of knot concordance. In case of knots, if I think of the set of equivalence clashes, concordance clashes of knots, and then I can think of the connected sum operation. Then actually this gives us an algebraic structure on this set. It becomes an abelian group, which is referred to as knot concordance group. And the goal is to understand the structure of this abelian group. Okay. Well, there have been several interesting, remarkable results to investigate the structure of this thing. Say, C. This is not a category in this talk. Okay. This is simply my abelian group. Probably I have to mention Levin's work. Well, he considered some abelian invariants. Well, by means of an abelian invariant, we think of some coefficient system, namely group homomorphism of the fundamental group into not only G, into an abelian group. In general, the involved fundamental groups are far from an abelian group, but it's a kind of simplification of the situation. And he extracted some very interesting algebraic invariants by considering such abelian coefficient system. And actually his invariants are enough to classify the knot concordance group in higher dimensions. In the classical dimension, well, Casson and Gordon proved that Leibniz invariants are not complete to classify the non-concordance group, and they used next level, namely Machiavellian invariants. Well, in other words, they thought of a map into Machiavellian group, which is defined to be a group whose second derived subgroup is trivial. So this is just the next level to the abelian group case. And in their 2003 Annals of Math paper, Cochran, Orr, and Teichner used much bigger groups G. Well, it was a kind of groundbreaking idea, and well, in order to extract invariants using these coefficient systems, we need some kind of tool to deal with these groups. But if the group is bigger, then it's not easy to deal with these invariants. So from now on, let me talk about the primary invariant considered by Cochran, Orr, and Teichner. Well, that's something I want to not very specific. So pi 1 of, for instance, we can think of pi 1 of this manifold MK, exterior, not exterior, or zero surgery manifold over not. Or sometimes we have to think of pi 1 of the complement of the concordance or slice disk exterior. So there are some technical stuffs involved there. Basically, but we want to map every involved pi 1, for instance, pi 1 of this complement, or the complement of this cylinder to certain common group G.
Also, Z2 is that I don't know which one derived in this one.
Okay, that's a good question. So the convention is G0 is G itself. That'll make things clear. And G1 is the commutator subgroup. Okay? Right. This is, I'm defining now. G plus 1 is just the commutator of the previous terms. So this is the derived subgroup, and the low central subgroup is defined by replacing this by G itself, not Gn. Okay? So this is my watch. This lecture room is perfect except that there is no clock back there, so I have to be careful. So let me now talk about von Neumann.
처음에 intention not to.
Oh, I see. He doesn't want to disturb, or I see. So I will respect his policy. Okay, that's very good to not to have what clock here. Well, one of the most surprising aspects of the work of Cochran or Teichner is to use their use of this new invariant, which is referred to as usually Cheeger-Gromov row invariant. So, well, originally, Cheeger and Gromov defined this invariant by choosing some Riemannian metric on the given three manifold and then use some analysis to extract a real number, and then using some spectral argument, and then later by using some index theory, one can conclude that the resulting eta type invariant is independent of the choice of the Riemannian metric. But the clever observation of that's, I think, due to Schumacher-Weinberger. It enables us to define this invariant as a kind of signature defect using some bounding for manifolds. Let me talk about that. So I need to use the von Neumann group algebra. Of a discrete countable group gamma. So this is a kind of analytic generalization of the ordinary group ring, let's say G gamma or C gamma. This is something used in Honda's talk. So it was referred to as something scary or strange or whatever you mentioned. So, anyway, so I have to use, I'm a kind of people who is using this kind of thing daily, and so this is something very familiar to me. So this is a kind of ring which contains this group ring. Of course, well, if this is a course lecture, then I have to define it, but I won't because of the lack of time. But the nice thing of this ring is the following. There is a dimension function.
What is the discrete countable SF? What is it?
Group. Sorry. I have prepared the computer talk or practice more writing. So for any finitely generated module over von Neumann group algebra, we can assign a real valued dimension. This is the very, well, if, for instance, if gamma is a finite group, then instead of this, we can think of a complex dimension. The complex dimension of a finitely generated C gamma module will be finite if gamma is a finite group. But in general, we have to deal with bigger and bigger and bigger groups, and so the complex dimension is not well defined as a finite number. And so, but this machinery enables us to think of real valued dimension even when gamma is infinite and very large. Okay? So given a three-manifold and a map from pi 1 of m into gamma, just suppose that I can find a four-manifold W bounded by M, and suppose that this gamma structure extends to W. Then I can define the intersection form twisted by this von Neumann group algebra coefficient, namely on H2 of W and gamma. This is kind of local coefficient of homology group. But it still allows a duality theorem, Poincaré duality theorem. And so we have the intersection form whose value is in now n gamma. And then using spectral theory, it decomposes. We can find a decomposition into, well, a positive definite part, negative definite part, and the singular part. This is the generalization of standard theorem in linear algebra. So now we can think of the dimension, L2 dimension, which is a finite real number now. So now the L2 signature of W is now defined to be the difference of the L2 dimension of the positive definite part minus L2 dimension of the negative definite part. And then now we think of a signature defect, namely for the originally given three-manifold endowed with the coefficient system, now we define this to be the difference between this L2 signature of the bounding four-manifold minus the ordinary untwisted signature of the four-manifold W. Then by using some index theory arguments, we can show that this is well defined independent of the choice of W. And one thing which is not very clear at this moment is the existence of this bounding four-manifold W. But as I told you, Schumacher-Weinberger's argument can be used to reduce the given general situation to that situation, that special situation where we have a bounding four-manifold W, so that the L2 signature invariant, L2 signature defect can be defined in any case in this way.
The second signature is just ordinary.
Right, exactly. Untwisted ordinary. Right. So in general, this is real number minus an integer, and so this is a real number, okay? So, well, let's see. Right, exactly. Right. That type of argument can be used. Actually, the proof of the index theorem in this setting is almost the same lines. The Boldism theoretic argument can be used to prove the index theorem, the required index theorem. Well, using this invariant, Kakrano-Tykra obtained an obstruction to being a slice knot. Namely, let's think of the zero surgery manifold MK now. And then suppose that I have a coefficient system like there. And suppose that this factors through fundamental group of the a slice disk complement. Namely, we assume that K is slice, okay? And then we want to derive a condition. Then suppose that the given coefficient system factors through this. Actually proving that this extension property is not trivial, but let's just assume that, okay? Then the associated L2 signature is trivial. This is their obstruction, but we need a very technical condition that on the coefficient group gamma, namely gamma is so-called PTFA. It means poly-torsion-free abelian. Let me explain what this is. It's getting technical, but it's essential. It's very essential condition in dealing with this kind of problem. I will try to give an explanation about the essential idea. So, a poly-torsion-free abelian group is none more than a group which admits a series, normal subgroup series. Such that each adjacent quotient is, as you can expect now, torsion-free abelian. In particular, this gamma is torsion-free. Well, here torsion means a finite order element in a group. So essentially, it forgets this setup. In this setup, we must forget something, namely contribution from torsion elements, finite order elements from the fundamental group, or this coefficient group gamma. This is a very significant restriction on this theory. So let me tell you why we can prove this type of theorem, obstruction, and why we need this condition. That's very, very essential. Okay, so let's see. The key idea is as follows. I have my M, MK, whatever. And suppose that I have a nice bounding four-manifold. Let's say slice disk exterior. As required, as we assumed in this as a hypothesis, then using this thing, I want to compute the row invariant. Okay, so this extension requirement is satisfied as we did there, and so now I have to show that this term vanishes for this W. Okay, that's the idea, main idea. Then, well, indeed, an easy homological argument shows that HI of this pair, homology, integral homology of this pair is trivial up to dimension 2. In particular, H2 of this pair is trivial, but just observe that the intersection from the non-singular part of the intersection, ordinary intersection form of W is supported by this group. But this is trivial. So the non-trivial part of the intersection form is trivial, and so this part, the ordinary signature of W is trivial. So the remaining thing is to show that this L2 signature of W is trivial. We want to apply almost the same idea, namely we want to show that the von Neumann group algebra coefficient homology is trivial. Then this term will vanish as well. This is the typical idea, the standard idea and approach, standard approach to extract slice obstruction or homologic cobordism invariant, starting from the work of Levin. And Kelson-Gordon invariants can also be interpreted in this way. Anyway, so in this context, but this is still open. We don't know. So then, what did they do to deal with this problem? If gamma is fully torsion-free abelian, then their key ingredient was that the ring, group ring G gamma, admits a skew. In general, gamma is not an abelian group, so I have to think of a skew quotient field. In general, an integral domain in the commutative algebra world, an integral domain always submits the quotient field. This is a non-abelian case, but even in this situation, it satisfies this ring. It turns out that if gamma is PTFA, then this guy has a nice algebraic property, namely it admits a skew quotient field. Quotient skew field, which one is right? Whatever you like. So, this is a field, and so it has a very nice homological properties. For instance, it's flat. So it's very easy to deal with homologies, homology group, homology modules over this skew field. And then we can, in this situation, instead of this, using this k coefficient, they prove that hi of Wm K is trivial. This was the main technical key ingredient. And then from this, well, they proved that, because this is a field, for any module over this thing, we can think of dimension. Everything is free. And so they proved that that dimension is the same as the L2 dimension, which was originally defined using analysis. So this is a kind of algebraic translation of the analysis setup to some sort of algebraic setup using the existence of the field.
So that dimension is not integer?
That's an integer now. So this is just only for polytorsion free abelian groups. That's the key point. Okay? Well, so
What's an example of PTFA which is not like
well, for instance, for any knot group, if I think of pi mod pi n, where this is the ordinary derived series, then it turns out that this is PTFA. So basically, this is an iterated extension of the free abelian group by torsion free abelian groups. But it's obvious that a torsion free abelian group can act on another torsion free abelian group in a non-trivial way. So then that extension is a non-trivial extension, which is not a direct sum. So it's very easy, not difficult to produce polytorsion free abelian groups with an arbitrarily given length. We can think of a shortest length for a given polytorsion free abelian group. It can be arbitrarily large. So this kind of group is not very special.
So, skew field is not abelian.
Right. Right. So it's a kind of more complicated non-abelian algebra world. But we can do many things even in this non-abelian situation, non-commutative situation. For instance, we can do a lot of homological algebra arguments. So that's possible.
So you mean that this result just proved by algebraic argument?
This is purely algebraic.
Purely algebra?
Right. Nothing about L2 theory.
So differential is not just the extension.
The differential is just from the, let's say, chain complex structure or whatever.
And then you just take a tensor product.
Right. Actually, there is an algebraic analog of this property for chain complexes. And this is just actually a corollary of that algebraic result applied to the cellular chain complex.
So let me translate. So G, this group ring is supposed to be abelian, isn't it? No?
Which one?
No, G sigma, G gamma.
G gamma? No, when gamma is a non-abelian group,
Oh, gamma is
G gamma, right, in general. I want to, that's the story of Jerry Levin in the 60s. It's 2000, and so we have to deal with something more than abelian's case in order to survive. Oh, that's a secret. Just to forget it. So, anyway, how long do I have? Well, I guess that many of you are not very familiar with this kind of story, and so I'm consuming more time about the background and the known ideas. So then, what's new? Well, the main new result I want to talk about today is a kind of new approach to this problem. It's more L2 theoretic, less algebraic, and it generalizes this kind of results for PTFA groups to some significantly larger class of groups. And it will, if I proceed as I planned, then probably I can give you some applications of this new technique. So, this is joined with, usually this is something I should mention in the beginning of the talk. But so far I just described some known results, and so Cantor at Indiana University. So, if gamma is amenable and in this part, let's just get rid of this part. And because I have to compare it with my new result, let me move it to here. Well, suppose that gamma is amenable, and in Strabel's class DR, where R is a commutative ring. Well, I will explain soon what an amenable group is and what the class of Strabel is. Okay? Then if the R coefficient homology vanishes, then we want to show that, as I told you, we want to look at this thing. I want to, of course, as I told you, if I can conclude that this is trivial, then that will be great. But I said that that's open. Well, I proved no new theorem during this talk, and so it should be still open. So then, what can I do? What I did is actually as follows. I can prove that the L2 dimension of this homology is trivial. I don't know whether this module is trivial, but I can show that its dimension is 0. And look, I want to, in order to compute the L2 signature, I look at the intersection form on this guy and then count the dimension of the positive definite and negative definite part. In order to show that the signature is trivial 0, it suffices to show that the L2 dimension is 0. So this theorem enables us to generalize this result to the case of groups which are amenable and in Strabo's class DR. So now probably I have to explain what this means. Okay? I will just give you. For instance, in general, if I have a short exact sequence, then I have the expected addition relation. So otherwise, I won't call this dimension. Okay? So in particular, dimension of this thing is bounded by dimension of this thing. So when the dimension of this is 0, dimension of this is 0. A good point. Actually, when I proved this theorem first, well, I was not very familiar with this L2 theory, and so I spent a day to confirm that question, the question you asked. So I'm happy to observe that you also are on the same line as I did. And so definition is as follows. This little bit technical. So basically the first amenability is something about the analysis. And the condition that it is in the class DR is something algebraic. So this is definition, but it's not very easy to see what kind of groups are amenable and in DR from this definition. And so I'm just going to give you a very nice sufficient condition. If I have a series of normal subgroups such that this quotient is abelian, in particular this is solvable, and has no torsion, has only P torsion. It's a little bit imprecise, so has no torsion coprime to P. P is a prime here. So here P torsions are allowed. Then gamma is amenable and in DR, namely we can use the previous result. So this is much more general than the definition of polytorsion-free abelian group, and in particular PTFA implies that it's amenable and in D of R. So the previously known results are just special cases of this new theorem. So, well, this is I would say this is a kind of change of viewpoint from this previous algebraic argument to more L2 theoretic analytic argument. And in the proof of this theorem, we use heavily results of Wolfgang Luck about vanishing of L2 dimensions. And essentially, at the bottom line, we have to deal with some analysis of L2 theory. And this is kind of some unexpected result. So far, since Jerry Levin, everybody tried to prove the vanishing of these twisted local coefficient homology groups. We are not yet very successful in proving the vanishing of the homology group, but we can still show that through the invariance of the signature invariance. So for instance, we can obtain the following obstruction to being homology cobordant. Suppose that I have a R homology cobordism between M and M prime. And suppose that pi 1 M, pi 1 W, pi 1 M prime, I suppose that I have coefficient system. Which vectors through the homology cobordism. Yes. Oh, but in this case, this R is related to this prime, namely G mod P. Okay? Thank you for pointing it out. And of course, in this case, I assume that R is G mod P, G or Q or G mod P or G localized at P. This is G mod P. My notation is that this is G mod P, this is G localized at P. Namely, this is the subring of Q consisting of rational numbers with denominators coprime to P. That's the usual object in commutative algebra. Then we can see that the invariance of the L2 signature defect under homology cobordism. Okay? And well, in order to save time, let me just mention that a slice obstruction. We can also obtain a new slice obstruction using groups, coefficient systems into groups which are amenable and in DR. Well, still there is some non-trivial part to resolve, namely, how do we show that the given coefficient systems vector through the given full manifold? Actually, well, that's a non-trivial problem, and for the case of knots, there are some known techniques to use so-called Blanchfield duality theorems and other things to guarantee that the required extension property. And for the more general case of homology cobordism problem of three manifolds, actually we proved a more general machinery to resolve that problem. That's called the Vogel-Kohn local derived series. This is defined by myself and Kent Orr. Well, this is a kind of modified version of the ordinary derived series. Given a group pi, we define a series of normal subgroups. Well, I'm using the same notation as the ordinary derived series, but this is something different. And well, it has some nice properties. Namely, if I have a group homomorphism which induces isomorphism on homology groups, then it induces an injection. This is a kind of injectivity theorem which can be compared with the well-known theorem of Starling's, which guarantees an isomorphism on the quotients by lower central series. A similar theorem was proved by Shirley Harvey and Tim Cochran, but they defined a similar series, but that series has a disadvantage that it forgets too much. For instance, it cannot detect anything about torsion elements in the group, while our setup can be used to detect torsion information. And well, this setup provides some baronaturality, functoriality properties, and so on. But I think I cannot describe all of these nice things in detail. But let me just.
What is this homological boundary phi G isomorphism on H star here?
I mean, the group homology of these two guys. So this is just a group version of the previously concerned space situation. They are fundamental groups basically. And well, my plan was to list up several nice properties, but I don't have enough time, so this is the second property in my preparation, and I have to jump to the fifth property, which says that pi mod. But it should be enough to understand some applications of my main theorem. Is amenable and in dr. In particular, I can think of this as gamma. And then using this thing, by this injectivity property, it turns out that I can resolve this extension problem automatically. So the theorem is now as follows. I'm sorry for not giving full details. This is solved by this theorem. If M is closed to the manifolds and pi denotes pi 1 M, and let me denote the quotient map from pi 1 M to the quotient by the JaeChoon local derived series by Vn. Then I can think of the von Neumann-Rowe invariant associated to this quotient map. And this is now an invariant under R homology cobordism. So this is something canonically defined for a given three-manifold M. You also have some new obstructions. If K is red and describing this. So, as I told you, as well as this new invariant under homology cobordism, we have some kind of new slice obstruction, and then we can use these two theorems to find some applications. First, I can mention, it enables us to produce several interesting applications. One of them is about knot concordance, which was my motivational problem. So this is due to myself. There are non-slice knots with vanishing Cochran or Teichner signature obstructions. Now, so far, Cochran or Teichner obstructions is the best tool to investigate the structure of knot concordance group systematically, at least in the topological category. But now we can say something about something beyond the limitation of polytorsion-free abelian groups, namely, this result says that there are several non-slice knots which are not detected by the previous known techniques, including Cochran or Teichner obstruction. This is a very nice illustration. I would say this is a good illustration showing the power of the theory, the extension of the theory to the non-PTFA case. I will just finish by just listing some further applications briefly. Even in higher dimensions, we can find some interesting applications. We can show that there are infinitely many homology cobordism clashes within the same simple homotopy class. When the fundamental group has a nice torsion. I want to describe what nice means because I have time. But anyway, it's another very nice illustration of the new theory, because the previous theory can do nothing about torsion elements. But it enables us to prove when there is some nice torsion elements in the fundamental group, we can produce infinitely many different types of homology cobordism clashes, even within the same simple homotopy type. This is a kind of homology version of a well-known result due to Chang and Weinberger. And we can also produce similar applications in dimension 3 for 3 manifolds. In particular, we can prove this type of theorem, the existence of infinitely many so-called different homology cobordism clashes even for space spherical forms. Namely, these 3 manifolds have finite fundamental group. So using torsion-free tools, we can do nothing. Everything is torsion. The fundamental group itself is torsion. But even in that case, our machinery enables us to detect some interesting homology cobordism clashes. Finally, we can make also an application to homology cylinders, which was first considered by Habiro and other people to investigate the structure of finite type invariants. And actually, we can form a homology cobordism group of homology cylinders which contains the mapping cylinder group. And it was an interesting question to investigate the structure of that group. In particular, Morita gave a nice invariant of homology cylinders But using this kind of L2 theory, we can prove that Morita's homomorphism is far from, let's say, an injection. Namely, his homomorphism has a large kernel, giving an answer to Morita's question. Okay, so I have to stop here. Thanks a lot.
Questions? Mark?